Hi, today I will talk about how the Hellman key exchange algorithm work and how mine the middle attack happens in this situation and how to prevent such type of attack using digital signature. So in first code, I implemented a simplified version of the Hellman key exchange. So in the Hellman key exchange, first we need to pick two numbers, G and P. The P is a prime number. In this case, it's 23. And the G is the primitive root of module of the prime number. In real life scenario, this prime number is like 1024 bits, so way bigger than 23. And the bigger the prime number is, the stronger the encryption gets. So usually people use bigger prime number. And this function is for generating private keys and public keys. In this example, Alice and Bob generate their private keys and public keys, and they exchange their public keys and to get a same value, which they can use as symmetry key later on. So first, each person has to generate private key, which will be a random integer between 1 and p. P is the prime number. In this case, we pick 23. It's a small number, so there are not many options between 1 and 23, but usually if it's a bigger number, then there should be a lot more options. And public key can be calculated by g to the power of private key mod p. So Alice's private key will be called A private, her public key will be called A public, Bob's private number will be called B private, and his public key will be called B public. And they exchange their public keys. And in any type of encryption, the private key cannot be shared with other people. Private key has to be known by the person who generated or person who owns it. So in this case also, they exchange their public keys to calculate the value called shared secret. And the shared secret can be calculated by public key power to the power of private key mod p. So for example, if Alice wants to compute the shared secret, she has to take her private key and Bob's public key. And in Bob's case, he has to use Bob's private key and Alice's public key to generate this value. And after generating this shared secret, if these values are same, then they can use it to encrypt their messages from now on. So this is essentially how the Diffie-Hellman key exchange works. An attack called mines the middle attack could happen in this type of simple situation, and I will talk about how that happens. So this next code, I did the same thing, picking G and P 523 and generating private keys and public keys and shared secret for Diffie-Hellman key exchange. And here also, Alice and Bob calculates their private key and public key. But there's a man called John between the communication. And Alice wants to communicate with Bob, and Bob wants to communicate with Alice, but John is in between those communication right now, and the communication is not encrypted yet, so he can see and modify the communications. right now. And John generates his private key. It is possible because if one person wants to generate private key, you just need to know the value P, which P is publicly known value, so everybody can generate this private key. As well as when it comes to public key, you need to know the value of G and P, which are publicly known also. So John generates his private key and public key. And when Alice and Bob exchanges their public keys, John puts his public key inside of the message. And now Alice calculates the shared secret using John's public key, and Bob calculates his shared secret using John's public key. But they are believing that they are using, Alice is believing she's using Bob's public key, and Bob is believing that she's using Alice's public key, but it's actually John's public key. And also, John can easily calculate the shared secret using his private key and Alice's private key and Alice's public key and Bob's public key, because they are public and he can easily get it. And if Alice's shared secret and John's shared secret is the same, and as well as Bob's shared secret and John's shared secret is the same, now what John can do is John can pretend like Alice or Bob, and whenever Alice tries to send message to Bob, John can open the message, see the message, and even modify the message and encrypt it again and send it to Bob. And it works another way as well. So John can do pretty much whatever he wants to do with the communication between Alice and Bob. And there's one possible way to prevent or a way to make this type of attack difficult using digital signature. And in my example, I used RSA signing function. So this part is the same. I picked two numbers for Diffie-Hellman key exchange. This function is for private key. This one is for public key. This one is for shared secret. And this one is for generating private key and public key for RSA. And this one is for signing data. So let's take a look at this function. So when it comes to signing data in RSA, you need data and your private key and hash function. You put data in the function and get the value called hash, and you encrypt this hash using your private key. Now you get the value called signature. So this is how this RSA signing function works. And as a recipient, if you are a recipient, you want to use the owner's private key and the data that you got and the signature also you got to verify the authenticity of the data. And in this case, we use the public key for Diffie-Hellman key exchange as data to verify the authenticity of the public key. Remember, in this example, John put his public key. John pretended like he's Bob or Alice and put his private key as Bob's or Alice's public key. But in this particular scenario, we can prevent this if Alice knows what Bob's public key looks like, and Bob's they can verify the authenticity of their public keys. So in this function, they calculate their RSA public keys and private keys, and they generate private keys and public keys for Diffie-Hellman key exchange. And here R assigns her public key using, I assigns her Diffie-Hellman public key using her RSA private key, and Bob verifies the authenticity of the public key. And likewise, Bob signs his private public key, and Alice verifies it. Then this part checks if it's of those two public keys are verified. And this way, for an attacker, it's very hard. It's harder to kind of swap original public key with attacker's public key because the recipient will verify the authenticity of it. So this is one way to kind of make the attack difficult, but it's not the ultimate solution. Because in RSA, we also use public key, right? And we used RSA signing function to authenticate the public key for Diffie-Hellman exchange, but what about the public key for RSA signing function? We didn't do anything to this. So actually, it's possible for an attacker to generate those keys pretending like it's a Bob or Alice and do everything that Alice and Bob did by himself. So it's not perfect either, but this is where other technologies such as TLS, certificate authority, public key infrastructure, PKI play in. But from these examples, I think we are able to see the importance of digital signature and how to the importance of verifying and authenticate our keys. Okay, so this is it today, and see you next time.